Okay, so last lecture before review material on Thursday, and then the midterm next week. So homework C2 solutions are out there. Homework D2 is due this weekend, due Saturday. So the content from today's lecture should help with that homework for those who are still working on it. Some tips, there are some histogram hints provided in the homework assignment. Nowadays, histograms are a little easier to generate, so those tips may not be that useful, but make sure you histogram your random variate generator, not your random numbers. So if you get a histogram out and it's just flat, then you're probably taking the histogram of the wrong column. So this does happen. So we're expecting you to generate kind of interesting distributions, not just the flat uniform distribution. You generate the flat uniform distribution and then put that into your random variate generator, and then that will generate output for that should get a histogram that does not look flat. So if it looks flat, you're probably showing me the wrong column or the wrong data. The submission should be a document, so docx, or PDF, not just a spreadsheet with thousands of random realizations. So try to answer the questions in the, question 1, question 2 in the order that they're given there, and the sub questions, and then show me like summaries of like your histogram and so on. So you can upload that. If you use the spreadsheet, you can upload the spreadsheet separately as kind of a part to show your work. But the thing that's actually supposed to be in the document that is the main thing that gets graded should be something that, you could, hopefully your assignment fits on 2 pages or something. So it shouldn't be just, 20 pages of numbers. That's not something that's gradable. So that's kind of all that we're saying here. Otherwise, the assignments looking forward, there's ICAF. So that's the review ICA. So that ICA, sorry, I'm just fixing an audio issue here. That ICA, this ICAF samples from all of the previous ICAs, samples randomly from them. And as a consequence, it's longer, but you can take it as many times as you like, and it'll take the highest score. So it's meant to be a midterm practice. Then on Thursday, we'll have this midterm review and question sessions. So I'll bring kind of what I think are the kind of the greatest hits from all of the slides, the things that I think are kind of the most important takeaways from all of the lectures. And I can have that up on the screen and walk through that if nobody has questions. But if there are questions or things you want to work through and those sorts of things, that's a good way to use that time. So if you have those, bring those. And maybe ICAF will help you generate those in your head. And then we can just start with that. But if nobody has anything, then I'll just push through those slides. And then as questions come up, then bring them up and we can handle those. But that's kind of the plan for Thursday, just a midterm review. And we'll talk more about, midterm formatty stuff as well then. But as we've been talking about, it's a stage 2 exam. So Tuesday, midterm stage 1. Next week, that's 80% of your score. That's the individual exam, closed book, closed notes, 2 formula sheets, double-sided, hand produced. So if you want to graph something or whatever, that's fine, as long as you do it yourself. I just don't want you to take screenshots of the slides or things from the book and so on. There are old versions of old exams and solution sets available on Canvas. And so if you take that compliance test, that midterm, that lockdown browser compliance test, that should unlock the midterm module. You should get access to all of those resources. And then Thursday, then that's when stage 2 is open. That's the same exam. You don't get solutions. You don't get your scores. But otherwise, it's the same exam, but it's collaborative. You can work with anyone who is enrolled in the course. It's open book, open notes. Any resource that I've provided you, anything on Canvas, and then your own notes you can use. Again, it's the same questions here, but your total score will be 80% the individual plus 20% the group. That's how that works. I do actually plan on opening this, stage 1, not just Tuesday, but at least Monday and Tuesday. And then stage 2, I plan on opening Thursday and Friday. I'm still deciding whether Wednesday will be stage 1 or stage 2, but basically all week, one of the stages should be available. With stage 1, regardless of when it's available, if you start it, you'll have 90 minutes to finish it, unless you happen to be very close to the end of the availability. Then the availability will cut your time off early. But anytime during the availability, you can start stage one and then your timer starts. If you come here Tuesday in class to take stage one, then I'll have to kick you out at 75 minutes because there's another class coming in here. The 90 is just to give extra time for any technical issues having to do with Canvas or lockdown or whatever. So you don't have to come here for either stage. I will be here so that the room is available if you want a quiet place to take it, but it's a Canvas-based exam. So if you do come here, then bring a device that, like bring a laptop so that you can take it here. Otherwise, you're free to take it elsewhere. So that's the basic exam stuff. We can go over more of that during lecture F on Thursday. But any quick questions about the schedule? Okay. Or anything else? All right. So I want to get to the material that'll help you with that last homework. That's the primary thing that we're talking about now. But also want to make sure that we get to that Kolmogorov Smirnov that we missed out on a little bit at the end of last lecture. So quick review where we've been sitting is that, we've talked about these are the kind of vocabulary, the ones here that aren't really, really light colors. So, these kind of darker colored ones, these are the distributions that I'm hoping that you kind of know the key ways they're used so that if you're in a situation where you need an input model that matches certain situations, you know which ones to go for or how to maybe combine them. So in many cases, these will be available in a good simulation tool, but some of them won't be, or you might sometimes have to build your own that doesn't quite fit these. And so then the question that is before us is how do we get a simulation tool that doesn't already have these implemented to draw from random variates matching the distribution that we want. So that's what we're trying to move towards. So we have our input models, we chose them, we want to put them into our sim. How do we then generate those input models so that our sim does what we want it to do? And so if we have a probability density function, if we take the integral underneath it, we get a cumulative distribution function. This cumulative distribution function has the nice feature that if you invert it, so imagine I had a diagonal line across this and I folded it so that the y-axis becomes the x-axis and x becomes y, so that the input, I guess if you want to call it that, is now on the left. Then if I draw uniformly distributed random numbers from 0 to 1, if I plug them into the inverse CDF, then I get numbers distributed non-uniformly, and they get distributed like my probability density function. That is inverse transform sampling. That's what we want to do, and that helps us generate pretty much anything that has an invertible CDF, and that's a lot of probability density functions have an invertible CDF that allow us to do this. So we then talked about last time, how do you get these uniform numbers so that I can plug that into my inverse transform sampling? We said that there are, of course, programs that already have these things built into them, like Excel or MATLAB. And these programs may or may not give you access to the seed. So in Excel, you don't get access to that random number seed. So every time you open Excel, you get new random numbers because it's seeded with the time. But on MATLAB and in Arena, you do get control of that seed. So in Arena, some of you might have already noticed as you're starting to use Arena, if you generate output, and now there's some more help on Canvas for those who are having a hard time parsing, figuring out where to get the output out of Arena. You may notice that if you open up Arena, you run your sims, you look at the output. If you close down Arena, reopen Arena, run your sims again, you'll get the exact same output, even though there's random numbers. And that's because by default, Arena always uses the same seeds to start with. And so it uses a certain seed for replication 1, and then it has a way to generate for replication 2 a new seed, for replication 3 a new seed, and so on. But replication 1, by default, always uses the same seed. So that's why every time you run, if I had all of you do the muffin simulation, for example, you would all get exactly the same batches of muffins going into that muffin sim. And so you would end up getting the exact same outputs, just duplicated across everybody because it uses that same seed. So tools like Arena do give you the ability to edit the seeds so that you can generate new replications, or you can coordinate better how, like if you've got two different models, you want to make sure, like in the muffin sim, you've got one batching policy, another batching policy, they both get the same muffins, then you can manipulate those seeds for you. So having the ability to control the seed is a useful tool that differentiates this a little bit from the randomness you get in the real world. There is no random number seed in the real world, but it's a tool that we can use in these computational systems to allow us to rewind universes, to replay them, to transport one universe to another location where we could run a different model on it, and so on. So that's why it's important to have control of these seeds. And so we'll see more of this, I think, after the midterm. But just so you know that if as you're starting to open Arena, and this is not stuff that I'm expecting you to memorize all these things, but as you're building expressions in Arena, as you move forward to these different labs, anytime you see one of these things that references a random number distribution, like uniform, triangular, expo, they're all going to take the parameters of that random number distribution, of that probability distribution. Like uniform takes min and max, triangular takes the min, the mode, and the max, and so on. But all of these have an optional parameter, which is the stream ID. And these are the things that you can configure inside Arena. So throughout Arena, and this is just giving you context, anytime you draw a random variate, you can tell it what you want your random number source to be, and you can then control the seeds. So you can say, well, I want my arrivals to be seeded one way. I want my services to be seeded another way, and so on and so forth. And that allows you to control sources of randomness throughout your model. And that becomes a very useful tool as you're trying to control for different things like, are these differences due to my algorithm, due to my model? Are these differences due to random luck because I've got a different set of customers coming in, and so on and so forth? So that's one of the reasons we talk about seeds. How does that connect to Arena? Well, every time you draw random variates in Arena, you have the ability to update the streams, and every one of these streams, you can configure the seed. By default, the stream 10 in Arena, that's the default random number stream. So if you don't have this argument in Arena, you're implying there's a 10 there. So if you edit random number stream 10 in Arena, you can then edit the random numbers that are drawn automatically throughout Arena. So if you notice that your sim keeps producing the same output of your roommates, then you can go into yours, you can edit random number 10's seed, change it to whatever number you want, you just come up with a number there. And then if you rerun it, you'll start getting different numbers than your roommate, because now you're using different seeds. So that's what we mean by seeds. It allows us to change the way we draw random numbers. Okay, so we mentioned that last time there are two important properties that every pseudo-random number generator must have. What are those two properties? What's one of them? Uniformity. What's the other? Independence. So uniformity and independence. And so we see up here that we've got, these are bad down here because they are not uniform. There are a bunch of repeated values. There's a bunch of values near 0.2 and a bunch of values near 0.7. So there's a bunch of values that are left out. So there's clumping. So these are non-uniform up here. And then down here, these are not independent. And we know they're not independent because there's a pattern. You see that there's low numbers here, there's high numbers here. So They roughly are sorted. Another pattern, just as bad, would be if they were alternating. If it was always low, high, low, high. If there's any way that allows you to predict the next number from information from the previous numbers, it's a violation of independence. So we talked about that the chi-square test is one way we test for uniformity. And then just at the end, we talked about this so-called KS test. So there's this long name, Kolmogorov Smirnov test. And so that is an alternative to the chi-square test when you have very few samples. We're going to review those in just a slide here so that we're all on the same page there. We didn't get to it, but we're going to talk about it very briefly here, that there also are two tests that we use to test for independence. So there is a autocorrelation test, a kind of a self-correlation test that you theoretically can use to measure independence, but it's not very practical to use. So what we use in this class and what you should be expected to know for a midterm, which we'll talk about here in a couple of slides, is the so-called runs test. So there are two types of runs tests. There's the runs above and below and the runs up and down. I teach the above and below. There was a faculty member who used to teach this class, I don't know, 15 years ago, and she would teach up and down. And occasionally I would get, back when I gave paper exams, I'd get students coming into my paper exam. And even though I never taught up and down, they would then do a runs up and down test when I'd ask them for above and below. So it'd be very clear they like got her exam or something and learned her whole test rather than just watching a lecture video of mine or something like that. So I always thought that was very interesting. But those are two different types of runs tests, and just make sure you learn the right one for this class. And I'll only teach you one of them. I argue I teach the easy one. All right, so let's get to that. So test for uniformity, we just said chi-square or chi-squared test, or the KS test for small sample sizes. So this is our chi-squared example. I could give you, and this is something I could do on a midterm. I give you 30 numbers like this. They are, random order. They're just randomly generated. And the question is, are they uniform? So we might want to use the chi-squared for this. And so if I ask you, or if I imply that you should use a chi-squared, then at this point in the class, I will tell you how many bins to use. So after the midterm, it's going to be up to you to determine the number of bins. I might give you a hint, but then you might have to modulate that. But before the midterm, I'll give you that. So I'll say, use 4 bins. So that's just going to mean that if you had 30 observations, and the hypothesis is that they go from 0 to 1, then you're going to cut up the hypothetical distribution from 0 to 1 into 4 equal spaces. So this is another thing that comes up. There's a point of confusion, is that some students will look at this and they'll figure out what the minimum number is and the maximum number, and they'll come up with that empirical interval. And let's say the minimum number was 0.03 and the maximum number was 0.96. And then they'll do from 0.03 to 0.96 and they'll cut that up. That's not what you're cutting up. You cut up the hypothetical interval. So hypothetically, these are uniformly distributed from 0 to 1. That's the interval you cut up into 4. So we cut it up into 4, and there are 4 equally spaced bins right there. And then we count how many of these numbers went into each bin. And we're going to label this O1, O2, O3, and O4, the number of observations in each bin. So if we do that count, there'll be 3 that come to this bin, 4, 8, and 15. And then from there, then we say, all right, what would we expect if it was uniformly distributed? Well, if it was uniformly distributed, since there's 30 numbers, they should have an equal chance of falling into either of those bins because they're equally sized bins. So 30 divided by 4 is 7.5. So I would expect that I should get 7.5 in each one of these bins. So then I calculate my chi-squared statistic, which is just the difference between each of the observed numbers and 7.5, squared divided by that expected number. We'll talk about why this formula makes sense after the midterm. It's not arbitrary. There are good mathematical reasons that have to do with the central limit theorem, as everything does, and normal random variables. But for now, it it's just a weird thing because you've got a squared value in the numerator and a non-squared in the denominator, so it doesn't look like the units make any sense, but it's the right formula. So don't divide by expected squared or something like that. You divide by the expected value, even though you square the difference in the numerator. So you have all these squared differences normalized by this is the expected values. You add them together and you get a number. Bigger is sort of a greater deviation from the hypothesis. So in almost every statistical test, the test statistic, bigger means bigger deviation from the hypothesis. So the hypothesis was uniformity. So if this is a giant number, then we'd expect to reject uniformity. So that's, smaller is closer to uniformity, bigger is farther from uniformity. So we have to ask, what is big, too big? And that's where we go to our chi-squared table. I will give you this table on a midterm. But I will give you, all 3 columns and a bunch of rows. You have to figure out how to use the table. And the way you use this table is if I say, and I will say this, that we've got a significance level or a confidence level of 5%, so we want a type 1 error of 5%, then that'll tell you to go to the 5% column, the 0.05 column. And since there's 4 bins, there's 3 degrees of freedom. And so we'll talk about where degrees of freedom come from after the midterm. But with a chi-squared test, it's always the number of bins minus 1. And to make a long story short, it's because once you know how many counts are in the 3 bins, you immediately know how many are left over. So you don't actually have 4 degrees of freedom. You only have 3 degrees of freedom because you know the total count is fixed. So if there's 4 bins, you go to 3 degrees of freedom. And so then that tells us that 7.81, that is our threshold. Notice that as the number of bins gets higher, so do these thresholds. So, and that kind of makes sense because that's going to mean that there would be more terms in the sum. So we tolerate larger deviations from normality if we have more bins. So that's what's going on with this pattern. So this says we can tolerate a difference of 7.81. The difference we measured was 11.87. That's bigger than our 7.81. So we reject the hypothesis of uniformity. And we say these show a sign that they are non-uniform. So, or we will be wrong in saying they're non-uniform no more than 5% of the time. So these numbers, it would be very unlikely that they came from a uniform random number generator. That's our chi-squared. Any questions about that? To be a review from either 380 or 385. I always forget where chi-squared lands. Okay. All right. So then KS test. I've only got 1 slide on this. This is probably the newer one. If you have very little data, then you can't use a chi-squared because that expected count has to be 5 or more. So if your total amount of samples is 5, you definitely can't use a chi-squared. So in this case, what do? Well, in this case, we're not going to bin the numbers exactly. We're going to say if we sorted the numbers, if they're uniformly distributed, do they fall in the right spot for their sorted position? So if these 5 numbers, which are in blue here, these are the numbers that I'm not sure if they're uniformly distributed or not. So I sort them. And so in this position, then I would expect, regardless of what's here, then the green numbers and the red numbers, so the top row and the bottom row, those will stay the same. Those are determined by the number of samples. So if there's 10 samples, then this will be from 0 to 0.1. Because there's 5 samples, it's 0 to 0.2. So these are just little intervals that divide up the range 0 to 1 by however many samples you've got. So if they're uniformly distributed, we're sort of binning the expected side as opposed to binning where the observations are. So the idea here is, or rather than saying it, the chi-squared creates large bins and asks how many fell into those bins. The KS test creates small bins where we'd only expect one to fall. And it then asks, did one fall in that bin? Or is the bin empty? That's what the KS test. So it flips the logic around, but it's doing effectively the same thing. So if all of our points fall within the expected interval, then the KS test is probably not going to reject. But there's usually always one that falls outside the interval, which would mean it's not right in the right spot for being uniformly distributed. So if I look here, so what I'm going to do is calculate the difference. I'm going to see, is everybody inside your bin? And I do that by calculating the top row minus the middle row. That gives me this difference. The middle row minus the bottom row, that gives me this difference. And if any of them are negative, like the middle row minus 0.2, in that case, those negative numbers, I'm not going to use those. Like they're going to end up being dominated by positive numbers. So I'm not even going to bother calculating. You can, but just won't use them. So that's why there's dashes here. So these dashes indicate a negative number when you do top minus middle or middle minus bottom. So this is my row of differences from top minus middle. This is my row of differences from middle minus bottom. I look across all of these differences and I take the largest difference. So some books, like our textbook, will say take the largest difference in this row and then the largest difference in this row and then compare them. In reality, you just look across both rows and you take the largest difference. And in this case, it's 0.26. So what's that is saying here is there's this diagonal line, that's basically the cumulative distribution we would expect if they were uniformly distributed. It's a diagonal line. That's the CDF of a uniform random variable. It's a diagonal line, a ramp. And so if I sort the numbers and then I plot them against their normalized rank, so these are all my outcomes on the x-axis, and this is their rank on the y-axis. So this is 20% of the way, 40% of the way, 60% of the way, 80% of the way, all the way there. Then that is what we call the sample CDF. So what we're really plotting is the difference between our estimated CDF from our data and our expected CDF from our hypothesis. That's really what we're doing in this table, is to calculating the difference between those two, the sample CDF and the expected CDF. And this is saying that there is the maximum difference we see here is 0.26. That's the biggest deviation from the CDF is 0.26. There's the mathematics of this have to do with drunken individuals that have to wander their way from a bar to home. And if they start at the bar and they always end at home, then the question is, how far away from the straight line path could they get on their drunken walk? And you measure that deviation, and that's what they call this, a drunken walk. And that's effectively what this line is doing, is a drunken walk from the bar to home. And this is saying that the maximum deviation, given that you pin those endpoints, that's what we're measuring. And so so the 0.26, we have to ask, is that a reasonable deviation from the expected path? And that's what we look up on our table. I'll give you this table on a midterm. And then so again, I'll say, what's your type 1 error? I'll give you that. I'll say, well, it's 5%. So then you look in the 5% column. Now, the degrees of freedom in this one, because it's not count-based, the degrees of freedom are the number of samples. So we had 5 samples, so I look in the 5 degree of freedom row, and that tells me that my threshold is 0.565. So I compare that to 0.26, and 0.26 is under 0.565, so I fail to reject the null. This is what we call a high-powered test. What that means is it is extremely sensitive to deviations from the null. So that means that if it fails to reject the null, you have strong evidence that the null is true, or that there's not a significant deviation from the null. So if you fail to reject uniformity with a KS test, it's probably uniform. That's not the case with the chi-squared test. Chi-squared is not as high of a power test. The reason we don't use the KS test for large numbers of samples is that it's overly sensitive. As you get larger and larger samples, you detect greater and greater deviations, or your ability to detect deviations becomes higher and higher. It's like a magnifying glass or a microscope that zooms in on those deviations. And it is so powerful that if you have more than 20 samples or so, it's very rare that it's not going to do anything but reject. So even though that it's close enough for you, it won't be close enough for the KS test. So that's why we have to have the two tests. For the large number of samples, the KS test isn't useful at all because it always rejects them. So we use the chi-squared. For the small number of samples, chi-squared fails to work. The numerics just don't work out anymore for reasons we'll talk about after the midterm. So you go to this high-powered test, the KS test. Questions about the KS test? Is it clear how you apply this test? Yeah. Oh, I'm sorry. Uh-huh. You can actually make a conclusion with a high power test. With a standard powered test, and we'll talk about what power is after the midterm, we'll define that term. But what we're saying with a normally powered test, just your average statistical test, if you fail to reject, it might just mean you just didn't have enough evidence. So as a quick example, like if I flip two coins and I'm trying to test, is it a fair coin? If they both come up heads, then I'd say, well, I mean, a fair coin can come up heads twice. So in that case, I just never have enough data with two flips to reject any hypothesis about a coin. So that's what I mean, like I just fail to reject, but it doesn't tell me anything. But this is a special type of test where even with 5 coin flips, it gives you the ability for this type of test to be able to actually say that, oh, if this thing failed to reject it, then it's probably the hypothesis. Question? Yeah, so, and we'll see more of these, I think, after the midterm as well. But sorry I don't have these labeled, but so these are your outcome levels on the x-axis. So if I look up here, 0.05, 0.14, 0.44, here's the 0.05, here's 0.14, here's 0.44, here's 0.6, I'm sorry, 0.81 is the next one, and then here's 0.93. So all of these edges, all of the data is plotted on the x-axis. On the y-axis, this is what I call the normalized rank. So it is the position in the sorted order divided by the number of points. So this first point, this 0.05 point, that's the first point. So what's 1 divided by 5? Well, that's 0.2. So I have 1 divided by 5, 2 divided by 5, 3 divided by 5, 4 divided by 5, 5 divided by 5. And that's what we call the sample CDF. As we'll see after the midterm, this sample CDF is oftentimes more useful than a histogram. So your gut instinct, the first time you start doing statistics, is when somebody gives you data, is to plot a histogram. But as you get more mature in your statistics, then you start realizing that the CDFs are a safer thing to plot, and you start plotting these things. But you have to learn how to read these things. They're just not as readable as PDFs. But you don't have to worry about, like, are my bins too big in my PD or in my histogram? Are they too small in my histogram? There's all of these histogram level plotting decisions that you just don't have to make because you just plot the data and you look at how the cumulative distribution looks and you get all of the same information out. You just have to know how to decipher it. Questions about any of that? KS test? All right, great. So then I mentioned that there's 2 other tests we have to worry about, really just one, because this first one I'm going to basically tell you to ignore, but you should know the name. We also need to be able to test for independence. So even if we have uniformity, we don't have independence necessarily. There are statistical tests for independence. If you're doing a general test or a general kind of characterization of how independent or how correlated signals are to themselves, there are a suite of these things called autocorrelation tests. And autocorrelation basically means self-correlation. And it's the idea that if you take a time series, so a bunch of samples from a random number generator, and then you shift that time series a little bit. So you say, I look at the time series now, and then I shift it one sample later, two samples later, and so on to generate a new series. Then you see how well do those two series correlate with each other. So you can basically do a linear regression between the points in the non-shifted series and the points in the shifted series. And if they're independent, then there'll be no correlation. So there'll be no shifting that, you won't get any predictive ability from the past versions to the shifted versions. But if there is a violation of independence, then you will see correlation. The trouble is you don't know if you're going to see the correlation one time step down the line, two time steps down the line, 100 time steps down the line. So there are these parallelograms, these graphs that plot correlations for every one of these lags. And then they basically tell you how correlated they are at these different distances. And each one of these has a type 1 error associated with it. So these become interesting ways to kind of get a rough idea of what the correlation is in a signal, but they don't have a statistically rigorous way to give you one answer to say we have independence or not. So they're not that practical to use. By the way, there's another term that might be useful for you to know at this stage in your careers is the term white when referred to time series. If we refer to a time series as being white, what we mean is it has no autocorrelation. So if you've heard the term white noise, what white noise is it means that if you measure the noise now, it doesn't give you any ability to predict the noise at any time period in the future. And that refers to it being white. And that comes from these correlograms that come out of these autocorrelation tests. If you take what they call power spectrums, so if you look at how they're distributed across frequency, they're flat. And if you're distributed everywhere across frequency, then you're white. White is all colors. So that's that term. White noise means no autocorrelation. A white signal is an independent signal. It's a signal where previous data does not predict future data. So I want you to know this term, autocorrelation. That is a sign of a lack of independence when you have self-correlation. So an independent signal should not be self-correlated. So know that term and know that there are autocorrelation tests that are out there. We'll see some more of these when we talk about batching after the midterm. What we're going to practice or focus on here, so the last test that I want you to know along these lines before the midterm is this so-called runs test. And we use the runs above and below test, sometimes called runs above and below, and in our case, the mean. Some people do runs above and below the median. We're going to use the mean. There are runs up and down tests. Again, a previous instructor who taught this class, about 15 years ago would do up and down. I think up and down is a harder test, so I went with above and below. But if you look online, like if you just look up runs test, then if you don't specify, sometimes you'll find an up and down and sometimes you'll find above and below. They're very similar tests. They just do the calculations differently. So how does a runs above and below work? Similar to the chi-squared example, I give you 30 numbers. Now, if I give you these 30 numbers, I will, if I'm expecting you to do one of these tests, I will give you the mean of these numbers as well. So if you notice that I'm giving you a mean, it probably hints that you should be doing a runs above and below the mean test. So, but that would be, theoretically, if I gave you this on a homework, I might not give you the mean. And so you load this into your program of choice, and then you calculate a mean. And I get a mean of these numbers. So now I am going to convert each one of the numbers into a 1 or a 0 based on whether it is above or below this mean. And so for each one of those, I say like this one, 0.1839, that is below the mean, so it gets replaced with a 0. 3803, again, below the mean, replaced with a 0. 8629, that's above the mean, replaced with a 1, and so on. So now I have a string of zeros and ones. Now, going back to my coin flipping example, if these were independently distributed, then if I know the frequency of zeros and ones, I should be able to pick or predict the number of runs based on a null model that is independent. So basically, if I imagine I have a coin that is weighted so that it comes up heads the same frequency as this thing comes up ones, that coin is independent even though it's biased. So it might come up heads more often than tails, but every flip doesn't give me any prediction of the next flip. So I can use that as my statistic generator, as my null model generator. And I can say that unfair coin, how often would it generate strings of 0, 0, 0, or tails, 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 or strings of heads, 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 heads. So how often would we get a long run? So if I flip it 30 times, how many runs would I get? And that's based on an independence assumption. Then I'm going to compare that to the number of runs I actually got and then see if they're close. That's the runs test. So let's see how that works. So I'm going to calculate the number of runs here. So I've got a diagram here to make this easier. So here's the zeros and ones. Here are all of the runs. So there's a run 0, 0. So it's all zeros and then it switches. So then this becomes a new run, but then it switches. So this is another run until it switches. So notice each run is either a 1 or a 0. So in these 30 coin flips, I've got 19 runs. So that's the number. I just need to count how many runs. I don't care if they're zeros or ones or whatever, just how many runs do I get. So for the 30 coin flips, I got 19 runs. Okay, so the other thing that I calculated was the number of ones, 17, and the number of zeros, 13. That tells me in my null hypothesis how fair my coin is. So this is a coin that is slightly more likely to produce heads than tails. And so the question is, for such a hypothetical coin that is independent, how likely would it be that it would generate 19 runs when I had 30 coin flips? That's what the runs test does. So it turns out you can generate the statistics on that, and using rationale, which of course has to do with central limit theorem and whatever, you can figure out that for an independent coin, the mean number of runs is this formula. Now, these two formulas right here, I actually am not going to give you. So I would recommend you write these down on your cheat sheet or memorize them. They're a little ugly. They make a little bit of sense after you've done this for a while, but initially maybe just write them down on your cheat sheet. But the null hypothesis here is that if it's independent, this is the mean number of runs you'd get based on how many heads and tails are in that, how biased the coin is. So on average, we should get 15.7 runs, and this is the variance. So basically, there is a normal distribution of runs. It is centered on 15.7, and this ugly expression here, this is the variance of that distribution. Remember, this is variance. It's not standard deviation. We're going to have to take the square root of it for this next step. So be careful about that square root. So we have that. So now we calculate a z-score. So we're going to take the number of runs we measured, 19, and we're going to say, what's the z-score of that relative to our null hypothesis? So we subtract off the expected number of runs, and we divide by the standard deviation, remember, the square root of this thing. And that says it gives us a z-score of 1.2367. So we are about one standard deviation away from the mean. So it's our question of is that close enough to the mean for us to say that this is something that our null hypothesis of independence could generate? So we look at our table, our standard normal table here, and this is the table I would give you, and I would give you a so-called one-tailed table. So you know there's one-tailed tests and two-tailed tests. We can talk more about where one-tailed and two-tailed come from after the midterm, and we'll get into that a little bit more, but it's just traditional for me to give a one-tailed test. What that means is if I ask you for a 5% type 1 error, you got to look for the 2.5% row because you're only talking about one tail and you can have error on either tail. So I look in the 2.5% row and I look at the critical value of 1.96. Just memorize that number. For normal random variables, 1.96 comes up over and over and over again. When we start talking about confidence intervals, the reason why a confidence interval is twice the standard error of the mean is because 1.96 is almost 2. It's just like a famous number. But for now, it's in the table 1.96. So then I say, is 1.23 less than 1.96? Turns out it is, so I fail to reject independence. If it were larger than that, then we'd say that we get more runs than we would expect from an independent coin. Questions about that? That's our runs above and below. Turn the numbers into coin flips based on the mean. Then ask, do we get more or less runs than we would expect if it was an independent coin with those heads and tails? Okay. So I don't have a homework assignment for you to practice that on, but that is something that it's the one thing that I haven't asked you to practice that it would be fair game for me to ask about on the midterm. And I do think, write down these formulas because I won't provide these formulas down here. All right. Okay, great. All right, so now we can get back into stuff that'll help you with the current homework. Talked about the linear congruential generator. That was from the previous homework. Just the quick review. The formulas are out there. I think I've already beat you over the head with this enough, so I'm not going to spend a lot of time on it. Do want to remind you about the combined linear congruential generator. This is a way that we get really, really long periods. So we get a large number of numbers before we get repeats. We increase the independence of our random number generator while still maintaining uniformity with the combined linear congruential generator. But then that leads us up to, okay, so how do we start generating other types of randomness, our random-variate generators? So as you're starting to see in the labs with ARENA, that you've got all these areas where you can put expressions in. So we have a process block like this one. And in this delay area here, this is where you actually input your input models. This is where you put your activity durations. And so if you click down on these expressions, it's got a bunch of probability distributions that you're likely to use here, like expo is already available there. But occasionally you've got one that's not in its list. So occasionally you get something like this, and you're going to need to put your own expression in there. And so how do you learn to build these expressions? That's what we talk about in this lecture. That's what you're practicing on this latest homework, this homework D2. So this picture showed this earlier. You've got this coming out of ARENA, these uniformly distributed random numbers. Push those into the inverse CDF, and you end up getting this out. So basically, we're solving for the formula for this inverse CDF, for this quantile function. So how do we do that? This is what you practice on in this homework. So for a continuous random variable, we know that the CDF is just the integral of the PDF. So in that case, if I gave you a PDF, the first thing you have to do is solve for the CDF, being very careful about if the PDF is piecewise, being careful to not just integrate every piece independently, that the previous pieces have to be added to the future pieces, and we're going to see an example of that. And then once I generate that CDF, then I invert the CDF. So we're going to show an example of that, but you basically set a variable equal. You basically say R is equal to f of x, and then you solve for x. So now you get x is equal to f inverse R, and that is your inverse sampling engine. That is your random variate generator. And then from there, you can take random numbers that were generated from U01 that MATLAB or Arena or whoever gives you, plug them into that function that you just solved for, and the outputs should be distributed like you want them. So that's the overview here. So let's see an example. So let's say we wanted to draw exponentially distributed random variables. So those are the random variables we want. This is this exponential PDF. It's 0 everywhere below 0. And then once it hits 0, it pops up. And then it decays asymptotically back to 0. Okay, so we need to generate the CDF of this thing. So we want to integrate these two pieces. So here are our two pieces. So I've got this piece for x less than 0. Now notice in the bottom piece, I take all of the first piece from negative infinity up to 0, up to that switch point. And then I add this portion and its antiderivative from 0 to x. So I don't just take the separate rows. Like I actually take everything that is accumulated from negative infinity to 0 of this piece and add it to this piece. That's the key thing to remember as you're generating these CDFs. Now for this one, it's easy because this thing integrated from negative infinity to 0 is just 0. So I see that in this top piece, this is going to be equal to 0, and this is going to be equal to 0. So I'm just left with this thing. And this CDF, pretty much all the action is this second row. And so that's a pretty simple case. There's not a whole lot of gotchas there. What you do have to make sure you remember is your limits of integration. And so when I integrate this thing, and you might need to, you have to remember doing substitutions and integration by parts and all the little integration tricks sometimes to make these things work. But once you get your antiderivative, then remember to apply both of your limits of integration. And that's where this minus sign comes from, is because you're applying both of these things. And so the negative that pops out front and the 0 that ends up switching things around. And that's why you end up getting a 1 out front minus this exponential here. That comes from these two limits. But as long as you remember your limits of integration, this one is a relatively easy one to do. So let's look at a harder one. So, and as a review, if you're trying to remember how to integrate this is in the review that I'll leave in the slides, but you can basically let u equals this minus lambda t, du equals this, push all this through, and that substitution makes that integral a lot easier. So just a review from calculus. All right, now let's look at a more complex one. Okay, sorry, I was jumping ahead. Now that we have that CDF, let's go ahead and generate our exponentials. So we have the CDF back here. It's 1 minus e to the minus lambda x for x positive. And so we need to invert that. We only care about regions of the CDF that are non-constant. You can throw out any rows of the CDF that are constant. So this row up here, it's equal to 0 everywhere, throw it out. We're not going to invert it. Just get rid of it. You only invert pieces of the CDF that are non-constant. So this is non-constant, so we're going to invert it. And that's the only thing we have to invert. So that entire range is right there in that line. So what we're going to do is we're going to set R equal to that row, that second row there. And then we are going to solve for x. So that's all we did here. Set R equal to that. We solve for x, so we get this expression, x in terms of R, and then that becomes our inverse transform sampler. That becomes our quantile function. So that is our inverse big F right there, that thing there. So if we plug in uniformly distributed random numbers to R, we will get exponentially distributed x's. Now, there's a shortcut here, is that if you were to look up the formula that Arena uses, or most, MATLAB or whatever, for how they do exponentials, you'll often find that they turn this 1 minus r into an r. And that's just an optimization, because it's just lucky that If R is uniformly distributed, so is 1 minus R. So you can just replace the 1 minus R with an R. So if you happen to look up in a book or whatever, and you see that, oh, an exponential generator actually looks like this, that's because they've optimized this. So this is the formal one, and this is the optimized version that just saves you an arithmetic operation. All right, any questions about that inverse? Before we move forward with a harder example. And we're going to see what this histogram looks like and everything, then we'll move forward with the harder example. Okay, so we have that. So then we take our uniformly distributed random numbers up here. We plug them into that function we just solved for. For every R, we get an X. These R's are uniformly distributed. These X's, if we do their histogram, are exponentially distributed. So that gives us this nice shape here. We can plug that expression that we generated into ARENA if ARENA didn't already have an exponential. So in any one of those expression blocks, we can actually use this ARENA expression. And that's equivalent to this thing where ARENA's already done the work for us. But if ARENA hadn't built this, we could use this and we could get exponentials out of ARENA. So for ARENA, RA, that is its uniformly distributed random number generator. That gives you a number between 0 and 1. You plug that RA into this function, it gives you exponential numbers. So that's how we do that. So any questions about this, about where this histogram comes from? These are the histograms. We want histograms that look non-uniform in your homework. So if your histogram's flat, you're probably taking the histogram of the wrong side. You're probably taking the histogram of your R's and not your X's. Okay. So harder example, triangular distribution. So here is our PDF for the triangular distribution. It's got 4 parts. It's got the 0 part before the minimum. It's got the rising part from the minimum to the mode. It's got the falling part from the mode to the maximum, and then the 0 part after the maximum. So when we do the CDF, we should get something that is S-shaped, where it rises up to an inflection point at the mode, and then it starts decreasing, diminishing marginal returns up to the maximum, and then it's 1 from the maximum all the way out. So how do we solve for this? So we're going to do the exact same process. So we take the integral of this thing, but notice that I've got this set up like its own little triangle here. So I've got every row of this includes a contribution from the current row and all of the previous rows. So in the first row, I take the integral of the first row from negative infinity up to whatever point we're in the first row. But once we hit A, that minimum, then I flip to the second row, and now I've got the first row offers a constant offset to the second row. So I'm going to integrate that first row from negative infinity up to that A point, and then the rest of it, the variable part, is only from A up to the current X, and that's where the second row pops into there. And I do that, so for every row, that's why it grows. So it's not just the antiderivative of each row. You have to keep adding the accumulated parts of the previous rows. So the way that's going to look then, if I plug everything in, is this first row is a 0 everywhere. So that'll make this easy because all of these are going to disappear. But I have to plug this ugly thing into all these purple ones. And so I get that 0. But then now I've plugged in this purple second row into this second column, and this green third row into this column, and then this red fourth row into this column, and that's going to end up being 0 everywhere. So that's how I'm going to get this S-shaped entity here, is that I'm integrating from A to X of the purple portion only in the second row, but then in the third row, that just becomes an offset, and then I'm actually integrating from C to X. And so that's what's going to cause the shift in character of this thing. And it's going to be continuous because it'll rise up using this, but then it picks up where that left off and takes over with the green. That's what causes it to rise up and then take over. So it's like magenta up to the mode and then green after the mode. And it stays held up there by the constant magenta in this third row. Questions about that so far? Do you see where this triangular integration is coming from? That's the hardest part about this, is getting used to that. Simplify all that mess, do the integration and do the simplification, and then you get the cumulative distribution function that we were expecting. All right, so now that's basically what almost everything you need for the first question of the homework. The second question of the homework is to ask you to invert a CDF that's like this one that has a square in it. And when you invert things that are non-invertible, then you have to make some choices. So you can't invert a parabola because if you invert it, it's not a function, because the bowl that worked well in one space, when you flip it on its diagonal, that bowl on its side is actually two functions, one on top of the other, and you have to choose which function that you want. And we have to choose that based on the range of the random variable. So we have to see how to invert this thing. So remember that we only worry about rows of the CDF that are non-constant. So we're going to throw out the first row, and we're going to throw out the fourth row. So all we have are these rows here. And so then we're going to look at the ranges of X, and then that we'll plug them into here, and that will tell us the ranges of R that are associated with those rows. And so I've got my CDF up here. I'm only focusing on these middle two because those are the non-constant ones. And I see that X goes from A to C. If I plug that into this row, then I'm going to see that R is going to go from 0 to this ratio. In the next row here, X goes from C to B. So I plug that into that expression, and then R is going to go from this ratio, which fortunately is the same one as we found up here, all the way up to 1. So that's the way I break up my R range, which should go from 0 to 1, and it'll get split up the same way X got split up. So I've got these ranges here. So now I see that my desired inverse CDF is going to do the reverse mapping. It's going to map from this range to this X range, and this range to this X range here. So that's what I'm saying down here. So I need to choose my inverses so that those ranges work. So when I look at this then, and I say, okay, I'm going to set R equal to each one of these and then solve for X. So R, I kind of compressed everything together here, but I set R equal to the blue thing, and then I solve for X. I set R equal to the red thing, and then I solve for X. And those two pieces will be the pieces of my piecewise random variate generator, my inverse CDF. And so that's what I'm just pushing through down here. So this expression, I'm gradually trying to solve for X. And likewise, this expression, I'm gradually trying to solve for X. And that eventually leads me down here to this expression down here, where X is equal to this thing. And the square roots come from this square and this square. But notice, since there's square roots, I had to make a decision about whether this was going to be a plus or a minus, or this was going to be a plus or a minus. And I chose this to be a plus and this to be a minus. Why did I choose those? I chose those to make sure my X range was met. So I know that for this R range, from 0 to this breakpoint in R, then I want X values that go from A to values greater than A. So I need to add to A. So that's why I chose a plus there. I know that for this range, from this ratio up to 1 for R, I want X values that are B as a maximum and then less than B otherwise. So that's why I chose B minus that there. If I would have chose A minus that, I would get X values outside of my range. If I would have chose B plus, then I would have gotten X values outside of my range. So that's how I chose those. Mathematically, it seems arbitrary which one you choose, but to make it work as a random variate generator, you have to choose to keep it in the range. Questions about that? And that's the key question you have to ask yourself in question 2 of the homework, is you will have a quadratic. Do I choose the plus or I choose the minus? Okay. So then I can generate my histogram in the same way. In Arena, there fortunately is a tria function that has the min, the mode, and the max. And it will generate this nicely for you. If there wasn't, you can implement this ugly piecewise inverse CDF, but it really is a mess. So I just put it up here for your curiosity. You can review that separately. But fortunately, they've done it for you, so you can just use tria. But it is possible to implement these ugly things in Arena. Okay. The other fortunate thing is for all of the standard distributions that are out there, somebody's already done this for you. So if you go to Wikipedia and you look up standard distributions, and down the right-hand side of Wikipedia, there's going to be a table of interesting information about that distribution. And one of the things that they'll list there on almost every standard distribution is the quantile function, or maybe the inverse CDF, but they frequently call it the quantile function, and it's been pre-calculated. So for these four as examples here, then they've, here are these. And so you can just look them up in a book. I'm not going to ask you to, you don't need to write this table down. I'm not going to say you have to know any of these things. I'm just saying looking forward, you will occasionally have to calculate quantile functions yourself. You'll occasionally have to do this. Occasionally you just get a distribution that doesn't fit, the standard distributions, and you have to do this. But all the standard ones, somebody's already done that for you, and you can just look them up. So I'm not asking you to record this table. You don't need this table. You don't need to know this table, but just know that these tables exist. Okay. So any questions about that? Or we can close out. I just need to show you this for discrete stuff, and then we'll cover all of the important things that I want you to know before the midterm. All right, so let's talk about this for discrete random variables. We've already talked about this. We did a lab doing the Monte Carlo where you've got to practice this a little bit. If I give you a probability mass function, you also can generate a CDF from it. I definitely am going to have questions about this, about generating discrete random variables on the midterm using methods like this. So from any probability mass function, you generate the cumulative distribution function. You can invert the cumulative distribution function by flipping it on its diagonal. Here's the CDF. Imagine a diagonal is there, so you flip X and Y around the diagonal. Here's your inverse CDF. And then if you were to plot then a random number from 0 to 1, you go up and then you get your outcome. And those outcomes will have the distributions like the probability mass function that you started with. So the CDF gives you the boundaries for transforming this random variable into this random number into this random variable. This is also called the random dart transform, throwing darts at areas and then those areas turn into outcomes. So how big the areas are or how likely they are to catch darts, and that's how you change the probability of each one of those discrete areas. So we've talked about this already in Arena, and so this is something that I would remember this for the midterm, is that once you have one of these inverse CDFs for a discrete random variable, you can load that into Arena and it will do the random dart transform for you, but you got to give it the CDF, not the PMF, not the mass function. And the syntax for that looks like this down here, where because it's the inverse, it takes the probabilities first, outcomes second. So this disk for discrete, all the odd arguments, the first argument, the third argument, the ninth argument, these arguments are all the cumulative distributions or the cumulative probabilities. The outcomes associated with them are the even numbers. So you would say that, and here 0.2 goes to outcome 1, so 0.21. The next one, 0.7, everything from 0.2 to 0.7 goes to outcome 2, so 0.72. And then the last one here, 1.03. This also means that the disk function always ends in a pair that starts with 1.0. So that's how you put a probability mass function for a discrete random variable into Arena, is you load the inverse CDF into the disk function. So I want you to know disk and just basically writing out the CDF in this form. Other things here, I'd already talked about empirical CDF. I'm not going to talk about this too much on the midterm, and we're going to see empirical CDFs after the midterm, so I'm not going to spend too much time on that. But if you're interested in empirical CDFs, then there's stuff here. So again, I'm not going to worry too much about that for the midterm. There are special case discrete random variables where if you know the mathematical form of the probability mass function, you can be clever about how you come up with the inverse transform generator. Because if you know the symbolic form of the CDF, then you can go through this process and come up with a nice symbolic random variate generator where you draw a random number and then you ask, which outcome is it in between, and then use that outcome instead. So that's a more, symbolic, a more mathy way to do this, but it's only for these special cases where you've got that nice closed form. So that's where some of these come from. So when you get lucky about that, and there are ways to implement those in Arena. The only, I guess, other thing that I'll mention here is that there are random variables that do not have invertible CDFs. So you often have to, in fact, I don't even want to, I'm not going to talk about it in the midterm. There's a bunch of kind of waxing philosophical about advanced things that if you don't have invertible CDFs, what can you do and so on. I've put a bunch of details in here, but I'm not going to ask about it, that sort of stuff on the midterm. If you're interested in the advanced stuff, I welcome you to go through the slides and then feel free to send me a note and I'd be happy to talk about it. But the big things for the midterm, no disk, know how to invert a continuous random variable to generate those. Those are kind of the big things in the second half of this. And then know those tests for testing for those things. Okay, so let me just give you guys a quick clicker so you can get some credit, and then we'll do midterm review next time. So, I'm going to give you a numeric poll, and just to get you out of here on time, enter the number 4 for your numeric poll. If you enter any other number, you get no credit for today. But if you enter 4, you get credit for today. So 4 is the answer for your numeric poll. 4.